Hello, everyone. Raphael from HM Academy. I'm the DevRel here. Today we'll have runtime verification. They'll go over different hooks or different security or best practices for hooks and different tooling that you have to protect your hooks in other smart contracts using the form of verification. Please take it away.
Yep, thank you. So hi, everyone. Thank you for having me today. I hope you can hear me well. So I'm Paulina, I'm from Runtime Verification, and I'm going to present security debugging and formal verification for Uniswap v4 hooks. So a couple of words about us. At Runtime Verification, we specialize on formal verification. That is a security assurance technique. We are going to discuss what it is in a bit more detail later in this presentation. But in addition to this, we also do a good amount of open source tool developments. We develop tools for formal verification. We develop a debugger. I'm going to show those today as well. These are focused on the Ethereum ecosystem, but we also develop tools for other ecosystems as well. And we also do security reviews, help customers set up the security process, tests, FV, and this type of stuff. And some more words about myself. I'm a CTO at Runtime Verification, and before that, I also did some formal verification research and was at MakerDAO, also formally verifying some of the smart contracts. So here is the brief outline of today's talk. I'm going to bring up some security concerns in hooks, the existing approaches to security assurance, the tooling that is available, and more specifically, some of the formal verification-based security tooling that is Foundry compatible that we have. So I intentionally made this talk pretty high level, and it is going to be applied to Uniswap v4 hooks, but to a set of contracts just so it fits into this talk. But always happy to discuss this outside of it as well. And if you have any questions, please feel free to interrupt me at any point. Feel free to ask questions, or you can also ask them at the end of the presentation, whatever works best for you. So just to start, a very brief explanation for what formal verification is, just so you can answer the question of why are you here, or why should you care about this type of tooling. And in very short, formal verification is a technique that allows to mathematically prove that the code behaves as expected or correctly. And correctness here is defined with respect to so-called specification or properties. So these are generally just statements that describe what the code should or should not do. We will see an example of that later in the workshop, but essentially the reason why it is important is because formal verification provides you with these mathematical guarantees that the code behaves correctly, which are generally just pretty hard to get otherwise. So now moving on to the actual part of the workshop, and I'm going to do some live demos, which historically are not working very well, but hopefully it will today. So as mentioned, I assume that you guys probably do know how to write hooks pretty well by now. So I kept the scope of contracts and the Uniswap v4 specific things to be pretty compact here, just so we can spend more time talking about security. But as a reminder, to set the stage, I also have this diagram here that showcases some Uniswap v4 innovations and also the flow that we are going to be looking at from the point of security. So as a reminder, the primary innovation behind Uniswap v4 is, so first of all, the pool manager contract that allows, it is a singleton contract, and it allows deploying and interacting with pools without having to deploy a new contract for every pool. So before that, in order to deploy a new pool to, for example, trade some 2 tokens, the user had to use the factory contract to create a new contract, which of course incurred costs. With Uniswap v4, we can now use the pool manager contract to initialize a new pool and instantiate it. And that is something that a user can do using the initialize function that is also referenced here on the slide. So in order to instantiate it, they need to call this initialize function from the pool manager, providing some input parameters, like, for example, token contracts, or called currencies, like is and DAI as one example. Some other parameters like fees, and also the hook, if it is being used. So hook is the contract. They are flexible, customizable, and they're used to customize or specify particular pool behaviors. So the pool manager is used to instantiate a specific pool that corresponds to a certain key that is being generated based on these input parameters that are provided during initialization. And then hook can be sort of attached to it, so it can customize how certain functionalities is implemented in the pool. So in this particular example, during initialization, when the user calls it, and that is also a slightly simplified system. So generally, there are also router contracts, which usually are more user-facing, but just for the sake of this workshop, I try to keep it pretty minimal. So the user tries to initialize the code, the pool, sorry, in the pool manager. The pool manager checks if the hook that it's being initialized with implements this before initialize function. And then if yes calls into the hook, the code, the corresponding code gets executed. Then the initialization of the actual pool happens. And then if after initialize is present, then once again, that is being executed from the hook before returning. That is the flow that is pretty general in a sense that that's similar to how other functionality works, not only with regards to the initialize function, but also swaps, adding liquidity and removing liquidity, so all these other functions. So we have, now that we have this, we could also talk about some of the security-specific aspects or hook-specific aspects of security. So here I'm referencing some points from the presentation that folks from Open Zeppelin mentioned in the developer session that they did several sessions ago, which I also highly encourage everyone to watch. They are describing the library that they're implementing for people to use hooks. And also they do mention some of these aspects that I think have also been mentioned by the guys from Certora in the past developer session as well. So here I have a subset of them, just the ones that are relevant for this slice of security that we are going to look at today. So some of the important things to note is, for example, the pool count. So because hooks are being chosen by pools, they potentially can be used, the same hook can be used by different pools. And depending on the hook implementation, it may or may not be important to check if, if it's being initialized by another pool after it has already been, used by one of the pools. The other aspect is whether the token, the hook, handles native ease, because it also may or may not be handling it, and it should be treated accordingly. And there are also, of course, very important, as in all smart contracts, access control properties. So it is important to check if access control is implemented in the hook, also as has been mentioned by the folks who were doing these developer sessions before me. Unfortunately, projects got hacked because of the missing access control. So it might be possible that hooks functions can be called by external users who are not, for example, pool manager, which can lead to vulnerabilities. So that is one more important aspect to consider. Luckily for pretty much these properties and more functional properties than security properties, there is automated tooling that is available that can help check this consistently in the reproducible manner. And that's what we are going to talk about. So how can we check these properties? Now that we know what to look for, essentially, how can we make sure that the contract actually implements this accurately? So I have ranked these techniques according to confidence that I think we have in them. That is a bit opinionated, of course, and please keep in mind that I do work on automated tooling, so of course I rank it as something that provides more confidence. But the thing I wanted to say about manual review, that is in the leftmost part of this arrow, is that, of course, that is very important. That is something that we are doing at RV, and it is surfacing very important issues. The problem with it is that it might be inconsistent. It is very dependent on the person who is reviewing your code, whether they have experience working with Uniswap v4 hooks, for example. And another problem with it is that once the implementation has changed, it has to be re-reviewed. That is nevertheless a technique that is widely used. So here, in the context of the example that we have, what it would look like. So we see that we are, let's say we want to check the first property, which is whether the pool can be initialized, can be used by different pools. So in other words, it does transform into checking whether what do these properties implement, what do these functions, sorry, implement, and how does before initialize work or after initialize work in particular? Do they allow being called several times? So if you want to investigate this manually, what we can do is we can just look at the implementation. So the implementation I have here is based on this Uniswap hooks library that OpenZeppelin has implemented. And I'm using the contract that is called base custom accounting. So that is a base hook with some basic functionality that also implements some of the custom accounting features. So if you look at the code, so we see the pool manager, it has the initialize function. As expected, there are some checks at the beginning. Then we call the before initialize function on the hook that we are essentially initializing the pool with. Then something happens, which is the actual initialization of the actual pool. And then we call after initialize after emitting an event. If we look into this before initialize function that is implemented in the hook that I am using in this presentation, we will see that there is a comment stating that the stored key, that is a variable that is being set within the function, should act immutably because it is being used across other functions. So in other words, what it means is that this function is basically meant to be called once. So otherwise, this pool key can be overridden, which might lead to security issues or some other issues. So what can we, what can we infer from this review? It does look like it works correctly. There is a check on whether a particular variable is being set to 0. So it does look safe to me at the moment, but on the other hand, I haven't run this, so maybe there is some obscure execution flow where something else is happening. There is not, but there is a chance that that is the case. And if there was assembly, for example, that would be even more difficult to analyze if it is implemented securely. And also, as I have mentioned, because the code can change, it has to be reviewed again by a person, ideally the person who was reviewing it before, or has enough context to make conclusions about the security. So what do we have that can assist us, that can assist this manual review stage? Another tool that is more automated is a very automated tool, actually, is static analysis. So it is widely used. Slither is one example of such tool that is developed and maintained at Trail of Bits. It is very easy to use. I did find another scanner for hooks, and that is great because the problem with static analysis, there are twofold. So the first one is it reports a lot of false positives. It doesn't actually run the code, it just scans it. And what it means is that it just tries to identify patterns that might be vulnerable, and then it reports everything. So you actually have to look through all the issues. I think in that sense, it is somewhat similar to using this LLM-based security tools that also are on the rise these days, which is also a great assist, but this fatigue of having to go through false positives is something that people mention as a drawback of them. And the other problem is that, as I mentioned, they are pattern-based. So they can only detect things for which there is a pattern, for which the detector has been implemented. I don't know if Slither has any Uniswap v4 specific detectors. If someone is looking for an open source project to contribute to, I think that honestly would be a great help. I was able to find a hook scan, which I think is a tool developed by Logsec. So that's just something that I saw today. I think that is actually a static analyzer that is hook specific. Maybe, it's a good idea to reach out to them and, see if they're looking for a contribution. So that's something anyone would like to do. Just as a quick example, I have checked out the repository from this Uniswap hooks. I also added some tests to showcase, things I'm going to present today. But I also run Slither here. So that is an example of how it works. It takes a couple of seconds, honestly, so that's extremely fast. It just calls forge build, which is based on Foundry. We'll get to it. And what it does, it reports some results. So it identified some issues that I think are either low informative, judging by the color. So these are just some general issues that it reported. So one has to actually look through them. If there is a bigger repository, then that also has to be, someone has to do it basically. And they are, as I mentioned, do not seem hook specific to me. So what approaches do we have that allow us to check something that is more specific to the project, that is not just general pattern matching, that is not requiring a human to just look at the code line by line? And that is something that is unit testing and just testing in general. So that is where we go more into this demonstration part. So just to mention, we have forked the Uniswap hooks repository. It is open source, so our fork is open source as well. I have pushed the examples that I'm going through today, so please feel free to take a look at it, try to run it yourself. The tools we are relying on mostly are Foundry, so we'll get to that in a moment too. And the other one is Control. That is our tool for formal verification. These are instructions on how to install them. Installing Control for the first time might take some time, but generally it's meant to be user-friendly. If you are running into any issues, please feel free to reach out to me anywhere you can find me. So what is unit testing and what is Foundry? I have put a link to the Foundry website here, but essentially Foundry is the framework, a widely used one. You probably have seen it or maybe used it. That allows for a lot of things, generally script writing, deployment, but also testing and fuzzing. So that is the development framework for Solidity contract. A killer feature is that you can write tests in Solidity. So Hardhat is another pretty great framework, but it doesn't allow writing tests in Solidity. People have to use JavaScript. So I think developers these days generally find it easier to write tests in Solidity. And in our formal verification tools, we have also decided to go with this approach, just because it's easier for people to use. It's clearer. So the first step, I will show how it looks like in the IDE in a second, but basically the first step to writing a Foundry test is to define a setup function. So setup function involves basically setting up the state. So we deploy contracts that we are going to try to test. And so what I'm trying to do here is I'm trying to write the test for this property that we have been discussing. So whether the contract can be initialized or connected to a pool twice. So in the setup function, we deploy the manager, we deploy the hook. The hook is deployed at this special address because Uniswap v4 uses this very clever way of checking which functions are implemented in the hook. So we do all of this, we deploy 2 token contracts, and then we can, based on this, initialize the pool based on all of this information. The hook we deployed, the tokens we have deployed, and some other parameters that we can set according to however we want, basically. And based on this, we can write an actual test. So let's take a look at what it would look like here. The first step towards building it is to run forge build. That just compiles the project. There are some compilation errors, I think mostly coming from the test contracts. And so that is what I'm using. That is the general structure of the Foundry project. So there is SRC folder, which contains the source code, test folder with tests. There is foundry.toml file that specifies how it is being called. And then here in the control repository, I have the control hook test, which is the test that I wrote. That is generally just the adapted tests from Uniswap hooks, slightly simplified, so I can present it in this context in the time that I have. So as I mentioned, we do this setup. Some of these helper functions are defined in control utils, but these are also generally just based on v4 core helper functions. So they just help deploy code to a particular address, initialize the pool by constructing the key based on inputs, and calling the initialize function on the pool manager, generally as expected. And as you can see, deploying mint 2 currencies also just deploys 2 tokens and means some specific concrete amount of tokens. So basically, based on this, we have this setup function that just deploys everything, and then we can write some tests. I hope the screen, the font size is big enough, but please let me know if not. So first of all, an important thing that we want to check is whether we can try to initialize the pool using the hook that has already been set. Or maybe a simpler version of this that we can check first is whether we can initialize a pool that has already been initialized. But before we do this, one thing that might be reasonable to check is that we can actually initialize something. So before we check if we can do it twice, maybe we can start by checking that it can be initialized once. So for this, we have this function. As I mentioned, we have all these parameters, everything set up concretely in the setup function. We call the init pool function, it is getting initialized. And what we do then, we check this pool key variable that is being set in the hook in before initialize, and try to get all these values that should be set now. And what we do then, we just check that they correspond to what we expected. So what we have provided as input is now currently being saved in storage of the hook. For this, we use this assert equals. That is a so-called Foundry cheat code. Cheat codes are special functions that are provided by Foundry. You get them by inheriting from this test contract that is also provided by Foundry. You get this setup if you run forge init, which initializes a new project. So what we are checking here is that the value, the first value, that is the input parameter, is equal to the value we are reading from the hook. And the way for us to run this is to use the forge test command. So we call forge, we say forge test, --mt specifies the name of the test, and then we just provide the name of the function. And there we go. So we can see that the proof has passed. That means that initialize is working. What we can do now is we can check that if the pool has been initialized, then it should revert. So we shouldn't initialize pools twice. For this, we also wrote this other test that does the same thing with regards to initializing the pool, but then we know that it should fail. What we want to prove is that this execution is not allowed and that it reverts. The way for us to do this is to use this vm.expectRevert cheat code. That is another cheat code that is supported by Foundry. It essentially just says that we expect that the next call is going to fail, and that is what we want to prove. Or check, depending on the tool we are using. So for this purpose, once again, we can do the same thing, and then we'll see that it indeed passes. So if we have already initialized this pool with the same input parameters, then we can't do this again. We can write some more properties, we can write some more unit tests like this. We can, for example, check access control. That is also a pretty popular type of test that people are writing, which is great because it makes sure that this very important access control property is respected. So in this case, another thing we could do, we can define an address that we know is not the pool that has been initialized. And I think the function that I'm calling here is before swap. That is actually, if we look at these flags, we will see that it is not mentioned. So before swap is not actually implemented. So it actually should revert. But one thing that we can see if we actually look at the source code is that it's going to revert after checking the access control. So that is just only pool modifier is a modifier that is used extensively throughout this code base, which is great because it protects functions, including this important hook functions, from being called by unauthorized callers, causing exploits. So I suppose by looking at the code, maybe I can even take a look at it. So it is going to call _before swap function of the actual hook if it is implemented. But before this, there is this modifier called only pool manager that checks if the message sender, the person or the address who sends this transaction is not equal to pool manager, then it reverts with this specific custom error. And I think a very nice thing that Foundry allows us to do is, first of all, to specify the particular selector of the error in which with which the execution is expected to revert, which means that it definitely fails due to the access control violation, not because something else went wrong, it ran out of gas or something. And the other nice thing is there is the vm.prank cheat code that substitutes the message sender. So otherwise, if we call this function by default, as it's an external function, the message sender would have been this test contract, but that's not something we are interested in in this context. So instead, we create this unauthorized caller, make address, also another auxiliary function in Foundry that generates an address based on the key. And so we set message setter to be this unauthorized caller. We expect that it's going to fail with this particular function selector. And nice thing is that I think it's actually going to pass, which is true. And then in a very similar manner, I won't spend much more time on this, but basically we can also check that the function that has not been implemented, the hook that has not been implemented, like before swap in this case, is also going to revert with this selector. So, well, maybe I can run it just for completeness. But yeah, so that is, sorry. So that's passing as well. Now, that is very important. I'm not by any chance trying to say that unit tests are not important. That is an essential part of the project. I believe everyone should have them. They do help identify issues, but what is the problem with them? And now getting back to the presentation, the problem is that they only allow testing for a specific execution path. So they provide limited coverage, and in a sense that we can't really enumerate all possible inputs. We can't enumerate all possible currencies with which we are going to initialize the pool, but there are chances that there are branches that are just not obvious. For example, compiler insert checks. If you ever try to, there is a good chance if you wrote tests where, some variables values are getting added, that something is going to fail due to a potential overflow if you're using Solidity version 0.8 and later. And that is because compiler is inserting checks. So there is actually a branch, you just don't see it because that happens during compilation. And that is not the only case. There is assembly, there are just things that are not obvious when you look at the code. So there might be edge cases that are still not covered by the testing. And the way to handle this is by using these two other approaches that we have here. So the first one is fuzzing, that is also powered by Foundry, and the other is the formal verification tool that we have that is called Control, that is Foundry compatible. So how does it work? I misplaced this slide, but basically what I was trying to say with this is that we are only executing one execution path, only looking at it, but there might be more. So now, as for fuzzing, the general idea can be described by what is said in this tweet that you can see on the slide. So instead of just calling the function with a specific input value, like 0 or 1 or something else, we just call it over and over again with different values. So in a similar fashion to what is said in the tweet, basically the engineer or Foundry as a framework calls this function and calls it with like 0 being the address or 1 being the address or -1 or, well, depending on the input parameter, or some value that is not that is not meant to fit in this. So depending on how exactly the fuzzer is implemented, this may vary, but generally the strategy is to just try to generate as many values as possible in the attempt to actually identify some edge cases. So it is looking for values on like ranges, at the ends of ranges of input size, this sort of things. What it means is that it allows us to write tests such as the one that you can see here. So we have already proved that when we call initialize twice with the exact same parameters, the execution reverts. But what we are checking in this way is that we cannot initialize the same pool twice, but we still don't know if the hook can be used by two different pools. So what we can do now is we can get back to our example and we can write another function or another test that is now going to accept inputs. And what we're going to do is we are going to initialize it once with the same values as before, but then we are going to initialize it once again, but we'll provide different input parameters. And that means that the key is going to be different. So the pool we are instantiating is going to be different as well, but we still want the hook to revert because we don't want it to be attached to two different pools. Because these two are now, we do have two input parameters. We refer to this, and I think Foundry generally refers to this as property-based testing or property-based fuzzing. Foundry is going to fuzz over these values. So it's going to call this test over and over again for the particular amount of times that is specified, customized in the foundry.toml file, by default 256, which is not a lot, so recommend increasing it if you're using this in production. It's just going to call it over and over using different values for currency 2 and currency 3. And for all of them, it's going to check if we are still reverting. So let's take a look at what is going to happen when we run it, but also I already ran it because Foundry takes, the match test parameter takes a regular expression essentially, or like a prefix. And I think this, oh no, actually it was a different test. Okay, let's run this one too, sorry. So this, that is passing. I have set it for 32 runs, which is extremely small value. Please don't do this, but I have a point and I'll prove it later. So that means that it's still working. For all pools that we have managed to generate with all these different values of currency 2 and currency 3, it is still working, which is a better security guarantee, honestly, because now we are covering several execution paths. And not only we can do this for this, we can also check that before swap that is not implemented also fails if it's called with different parameters. So here I'm specifying as input parameters some values that are being passed as swap params. And it fails for all of them, which is something that we have shown before here. A quick note is that, so providing values as input parameters is one way to make them arbitrary. So we're going to fuzz over them. Another way to do this is to use cheat codes that look like this. So you can say vm.random address, it is going to return a fresh value. And there are some similar cheat codes for random uints, random bools, so you can do that as well. And a nice thing about it is that this, and actually all the cheat codes that I have mentioned so far are also supported by control. And I will explain why that is great in a second. So now just to, please feel free to also stop me if there are any questions, but essentially where I'm getting at is that we can execute different execution paths. That is good, a great way to identify some issues, but problem with this is that it's still not all of them. So there still might be some execution path that might be missing, that there might be a very tricky condition that we just can't identify. Yes, please go ahead.
Yeah, so I always wondered about the difference between fuzzing and form verification, but it seems so fuzzing is just like, as you said, like a range. So we're only gonna test with so many, and I assume form verification now like widens that spectrum.
Yeah, exactly.
Gotcha.
Yes. So thank you for this question. Basically, that is exactly what is happening. So fuzzing, as great as it is, and it's a very, very powerful tool, it still enumerates all this execution path. It still calls it with values that are randomly or pseudo-randomly generated, actually. And the problem is that we still might not hit some inputs that are just pretty hard to identify. So that is how we could use control. That is what control does. So control just proves it for all possible values. And it does not enumerate all of them because that's too long. That's impossible. You can't enumerate all U in 256 in lifetime. So that is not the way to go. What we do instead is we prove them mathematically. So I won't go into like too many details. I will get back to this diagram once again. But basically what is happening is we take the source code, and here's an example of a control proof, and it looks exactly like Foundry test that we had before. That is very intentional. We use it as the specification. So we are actually checking the things that are happening in this test. We want to make sure that this behavior is correct, is what happens at all times, under all possible circumstances, under all possible currency addresses. So what we do, we take this code and we transform it into a mathematical formula. That is a high-level explanation of what happens. So we translated it into a formula. We do have a formal model that we use to just being able to reason about this, because we need some representation of this that we can mathematically analyze. And for us, the formal model is the formal semantics of EVM. So that is just the implementation of EVM in the language that is good for reasoning. That is called K. That is just something that we develop at RV. We maintain it. We use it in client engagements. That is just an EVM, basically. It's pretty much a client. We are checking it against the specifications and tests that Ethereum Foundation puts out for clients. So we know it works as a client, but we can also just reason about it, mathematically prove things about it. And then we also need properties. And the property here, once again, is the source code that we are analyzing. So the property we are actually checking is whether the execution finishes successfully. So either it does not revert, or if a revert is expected, it reverts. If we expect an event, that is also one other cheat code that exists, one other nice property to check is whether events are emitted as expected. So we basically just use Foundry's success predicates. So whatever Foundry thinks is right, we use the same thing as the foundation of our formal verification, the issues we are looking for. And then we just feed all of this automatically to the formal verification tool like control. And then it either tells us that no violations are possible, or if it manages to identify some input in this whole space of all possible values, then in this case, it's going to report it back to us. And we'll also see how it looks like in a second. So that is the general idea. It does allow covering all execution paths. That said, formal verification is pretty resource consuming. There are issues associated with it, just challenges that are common for all formal verification tools that include, for example, reasoning about loops. If you have a lot of loops, then you may not be able to just formally verify it very well. If you have a lot of branching, it's going to just take a very long time. We do parallelize proving, which does help a lot, but generally there are some scalability constraints that honestly we partially mitigate by just providing the specification and only checking that what happens in scope of this function. So maybe I can quickly go through the what control proofs look like, but if there are any other questions, maybe I can take them now if you guys think maybe that's a good idea.
Yes, there's one question in the chat now for Juan. How does it handle path explosion?
Right. Yeah, thank you. That is a good question. That is pretty much what I wanted to mention in this in the previous point. So generally, what we do is, first of all, we limit the scope of what we are proving. So we are proving things within this test. So we aren't trying to check all possible function invocations, all possible sequences of them. So that is one approach to this. The other is, as I've mentioned, parallelization. Control can run proofs in parallel, and it can also run different branches in parallel. And that is something that we are using. I can send some links later, but basically, I think it was Lido. There was a code that in one of the engagements we had that is public right now, there were just essentially just a lot of branches. And we managed to reduce the time significantly just by parallelizing branch execution. So if you have enough cores, you might be able to, it probably will handle it pretty well. There are some techniques that can be used as well. For example, we can abstract some parts of the execution. So for example, if you are calling into, you have a proof, you're calling one function, it calls another function that branches a lot, but is not relevant to the property you're checking. What you can do is you can use some cheat codes that Foundry provides, for example, mock call and mock function. And that essentially just allows returning a value from this function, or it allows calling another reference implementation instead of this one. So in this case, you are not exactly still executing the exact same code at all times, but you're just abstracting part of what you're analyzing if it's not relevant. So that belongs more to the compositional formal verification, which is also just another field in formal verification, but you can just break system into several components and reason about them separately, I guess is probably the explanation for this. One last thing that I can mention is that that's not something that is very user or client facing, but the framework we're using allows writing simplifications. They look like lemmas essentially. So we can, in this key language that we have, we can write some statements that help simplify things. So if we see, for example, a very complex arithmetic expression that the tool automatically cannot handle, and under the hood control uses off-the-shelf software that is honestly shared by most of the formal verification tools, at least all, I think, in the Ethereum space. So it sometimes has issues with arithmetics being difficult, or catch-ups, for example, is also one thing that just inherently challenging for formal verification. In this case, if we notice it, we can just step in and provide some advice to the tool. So we can just set it some expressions that simplify what can be simplified, which we see as humans. And that is also the way in which, that is probably a bit more detailed, but I'll just mention it. So another thing we can do with this is write loop invariants. So as I've mentioned, unrolling loops is difficult because if the number of unrolls depends, or iterations depends on the parameter that is symbolic, meaning arbitrary. So it can iterate for like infinite amount of times. And we can't really check this, right? So what we do is either we just let it unroll several times. And we did identify some actual issues this way. So that is something that fuzzing, I think, is that is more difficult for fuzzing to identify this, because fuzzing would have to, you would have to build an input parameter set that forces it to iterate the specified number of times. In control, we can just specify the number of iterations, and then it's just going to happen for like 3 or 4 or 5 times. So we did identify some issues in this way. Or on a more advanced level, also something that we sometimes do help clients do, is we can write an invariant, which is also, once again, this formula, like the lemma, that just summarizes what happens within the loop. But that is a bit more challenging. So generally, short answer is the simplest way is to just parallelize the number of branches, make sure you're only calling things you're interested in, get assumptions if you want to restrict the input set. So maybe you don't want to check all currencies, maybe you want to check currencies that have a specific, the address belongs in a specific range for them or something like this. So I hope that did answer the question. And yeah, I'm sure, was there another one? Sorry, there is the only screen that I have that I'm sharing.
No, that was the only one.
Okay, great, thank you. All right, so maybe I can just very quickly show how control proofs look like. I have pre-ran them ahead of time. Every proof, as I will also show you guys, takes like a minute or maybe a couple of minutes to run. So it's not a lot, but just in the interest of saving time. That is, by the way, because I pre-run them, we are saving some artifacts when we run control. So I have a separate window, but generally that's just the same project for the most part. So similar one with the fast test that we had here. And so one thing that I can show to prove that I'm not making stuff up is I can take the same initialize already revert test that we were running with Foundry and run control proof on it. So similar to forge build and forge test, the commands that we use with control are called control build. That is similar to forge build. It does use forge build under the hood. And control proof. Control proof, similar to forge test, except it proves things and not just fuzzes over them. But otherwise, that is the same test. --mt is also the input parameter that we are using. We are trying to mimic the behavior of Foundry as much as we can. And another reason for this is, another thing we do to make it happen is supporting cheat codes. So we try to support as many cheat codes as we can. Some of the cheat codes were included in Foundry after we asked them to, so that we stay compatible with them. I think this random address is one example of it. So the proof passes. It takes 2 minutes and not this like 2 seconds or something that Foundry uses, but it proves that it's true for all possible values of currency and currency stream. And not just this. So another test, that is the last 2 tests that I'm going to demo. So hopefully we'll fit it in time. But basically, I was looking for something a bit more challenging. And what I did is I took the add liquidity function and just slightly simplified it so we can discuss it quicker, basically. So what we have here is, it is a small simplified implementation in the hook itself. So usually, like generally in the hooks, it is implemented differently. It involves modify liquidity calls into the pool, but that is beyond the scope of this presentation. Control can work with this. I just very intentionally decided not to. So what happens here is the user provides liquidity. If total supply of the shares of this hook, which is also an ERC20, is 0, then a certain amount of shares is being minted, same as the liquidity the user provided. If not, we calculate the amount of tokens that they should get. Then we add liquidity to the tracking variable of total liquidity, minting shares to the user, and returning. So that's about it, right? Another check that we have here is ensure that the deadline, that is an input parameter that we provide as well, is less than the current timestamp, because otherwise we are submitting a modification request that has already expired. So that's not going to go well, obviously. So that's it. That's the whole implementation. That's the only thing that we have here. And what we can do now is we can write a simple test that adds liquidity. We can specify some parameters. We can have arbitrary amount that the user is providing. We can set the deadline to be arbitrary as well and provide that as input. We can also make other input variables symbolic too. And then we can check what is the resulting state. Problem with this is because we are running everything concretely, the hook is in the state in which it was after initialization, right? So generally the storage of it, the state of it is zeroed out. So total supply is 0, no liquidity has been provided. So if we call it for the first time, then we are going to only execute this execution path that corresponds to this branch, right? Because total supply is 0, nothing has been supplied before. Even though some of the input parameters are being passed over. So it's not truly a unit test, but we are only covering this single execution path. not only that is the case, we can run it and the proof passes. If I increase the number of runs, sometimes it does identify the issue, but the problem that it doesn't find is that when we're submitting the request, deadline is just an input parameter. We have no constraints of this. It can be anything. And at liquidity, we actually do have a check that it should be less than the current, it has to be greater than or equal to the current timestamp. So it is possible for it to actually violate this. It is possible for it to be less than the current timestamp, but in 32 runs, and in more of them most of the time, Foundry is not able to find it. So the question you might have now is whether we can find it with control. And the answer to that is yes. It's going to take a bit more time because it's going to generate us a counterexample. During this time, I will also explain something else. So let's see how this works. Also, similar to Foundry, it executes setup first, then it calls, then it analyzes the actual test, and you can see that it is failing. And another thing that I wanted to mention is that another nice feature that is supported by Foundry and Control is the cheat code that is called set arbitrary storage. That is the last technical aspect that I wanted to cover. So what it does, it helps us assume that not only input parameters are symbolic or arbitrary, it also means that everything that we are reading from the storage of specified contract is symbolic as well. So when we read the value of total supply from this contract, it is also symbolic. We assume that total supply can be whatever, anything uint 256 can be. And what it allows us to do is to check that any deposit works correctly, not just the first one, not just the subsequent one, any of them. We are just going to have two branches in the execution, which we are going to see. So in this case, this proof is passing. We are checking as well that the state is adjusted correctly, that total supply is increasing, the balance of the user that gets shares is increasing, total liquidity is increased by the amount that has been provided by the user. So everything is the same, except we also need to consider that all these storage values now can have any possible value. So we need to make some additional assumptions if we want the execution to pass. So that is generally the structure of the proof. So first of all, we make some assumptions. We say, for example, the deadline we are submitting is greater than block.timestamp. So it won't revert on this check whether it has expired already. We also make sure that if total supply is positive, then total liquidity has also been positive, because that is just how it would work. And that also there is no overflow happening when we add tokens to total liquidity. Once we do this, it's just going to pass. And if we look at the execution, we'll see that there is a branch there. And now we have the output for this proof that was passing with Foundry. The one where we had no constraints on deadline. And I know that is not extremely readable. I promise we are working on this, so we'll have some updates on this soon. But the important thing that I want to show here is this path condition. So path condition shows the expression that needs to be true for us to get into this state where something is violated. So here, what it says is that the deadline variable, the input variable we have, is less than timestamp. So first of all, we can identify this in just a single control run. And the other point I want to make is that timestamp in control is also symbolic. So environmental globally accessible variables like timestamp, block.number, chain ID, I think chain ID is concrete now, but some other ones, nonce, for example, these are also symbolic, specifically to make sure that we also cover cases like this. It can be made concrete with Foundry cheat codes if necessary, but otherwise, not really. So I think that is pretty much it for control. One thing I wanted to just show very quickly is our debugger that we have. So if you get a test that is failing, but you want to make sure that it actually is, you want to reproduce it, or you want to put a proof of concept, what you can do is, well, obviously you can write a test with all inputs being hard-coded. And you can install Symbolic, which is our debugger. It's available in VS Code, and we find it pretty helpful. We also heard good feedback about it from people, so I thought I should probably show it to you guys as well. If you install it, you will be able to click on this debug button. It's going to start a debugging session. It's sending the compilation result to the server. And it takes a couple of seconds, but basically once it loads, we would be able to step through the execution line by line. It doesn't usually take this long, but I think the reason for this is because I'm showing this. But then on the left-hand side in this pin, you would see that there are values that correspond to variables. There is some also information about the contract. There is the EVM state, some values of the global variables. We can also see what, for example, the timestamp and number we are executing this with. And also, most importantly, we can just step through the execution. So once this line has been executed, we can see that the value of 2 was updated. And then same for ID. We can set breakpoints. We can step through function execution. That is a smaller function that I was using for debugging purposes. It doesn't work with, so the extension that is available in VS Code is not working with cheat codes, but we are also rolling out an update and a beta version. So I have a slide for this, but please reach out if you're interested in giving it a try. We're looking for more users to just give us feedback before we move on to the next stage of its development. And one final part, we also have a hosted Foundry and control solution that is called CAS. CAS is free to use. So if you are interested in running Foundry or control in cloud, please feel free to just go to cas.runtimeverification.com website. And what you would be able to do there is you would be able to just run it in cloud on our compute, essentially. And you will see the report that looks like this in the end of the execution. So what we can see here is the result of running the exact same test suite as I have shown right now. If there's a failure, you can see the same output as we have just discussed. Also the time of the execution and things like this. In the platform itself, you can run control tests, you can run Foundry tests. So once again, if you're interested in giving it a try, please feel free to reach out to us anywhere. Happy to guide you further into using this. We are just, giving it to users at this stage. So highly recommend taking advantage of this. And of course, just to wrap up, basically there are a lot of other things we can prove. We can prove correctness of tokens, we can prove native token handling, we can prove arithmetic correctness, which we do extensively as well in our engagements, that events are emitted correctly, that liquidity caps are enforced before ad liquidity deadlines are enforced, which is something that we have covered. So a lot of things we could analyze. As a reminder, so control is open source, it's free to use. We use it in production. It's compatible with Foundry, can be run in CI. Our clients do run it in CI. And just once to reiterate, the key points I want to make is that it's compatible with Foundry. It's not much more difficult to write control proofs than Foundry proofs. And it can continuously check, even if the code gets updated, that the formal proofs are still passing. And we keep maintaining it. So it does get UX and performance improvements that our clients actually do benefit from. There is a GitHub action that you can see here on the slide that installs it into your CI. And generally, there is just way more stuff than I could fit into this presentation. We have our cheat codes. We can show proofs, manipulate proofs, so a lot of different things actually. And CAS is the host solution that I have mentioned, works really well with CI. It helps save some time on consistent runs of CI because we cache proofs and it allows sharing this. You can use the report that is being generated with general public to prove that the code has been formally verified. So yeah, there's generally just way more stuff. That we have some libraries of proofs for ERC20 contracts that can be reused, and generally just way more stuff than I could mention. So the final thing I guess, is that Symbolic, once again, an EVM debugger. I put some links here if anyone is interested in trying. And here is the Telegram channel that I think is actually being used pretty actively. So if you run into any issues, if you want to try the beta version that we're going to release soon, just drop us a message and we'll be happy to talk. That should be it for my presentation. Thank you so much once again. Thank you for the questions. And yeah, these are some of our socials. Happy to answer any questions too.
Cool, thank you so much. If anyone has any questions, please go ahead. This is really cool. I love the fact that it's like it's pretty much Foundry, but that's your twist. So I don't have to learn anything else. I'm already used to using Foundry. So I get to just jump in and start running some form of verification.
Thank you.
Yeah. I guess also I had a question. So the power that formal verification has is it can go down every path, but that path also slows it down and it can make things take forever depending on the actual loops or whatever that may be happening in the functions. So the main thing is to like really be precise with the scope of what we're doing and like what you're looking for per test, right?
Yeah, exactly. That is what we recommend people to do. That is also what we are telling our clients. We can't promise that we'll formally verify everything, like every possible interaction people might have
Right.
with your contract. But there are just things that are more amenable and make more sense for us to verify, like access control, for example. That is a pretty straightforward property. It's usually not involving any complicated execution path. But it is important. So that is one very easy thing that, I guess pretty much everyone can just add control to the Foundry proofs, the Foundry tests they hopefully have for this. Mathematical libraries, like standalone libraries that, for example, have no dependencies but contain important code, is also another thing that could be checked. Equivalence check-in for functions that are written in Solidity and we know are look safe. And the same implementation in assembly, for example, we can also check equivalence between these two things formally. Usually as well does not involve going down too many different paths, but is just a really safety critical piece of software that would be good to verify. So yeah, as you've said, just scoping out the most important part that just makes sense for us to prove.
Cool. I do see a question. Thank you. Nice. Yeah, thank you so much everyone for joining. Thank you, Pauline. Thank you, Runtime. I love this tool. I can't wait to give it a try, and hopefully everyone else is interested in checking it out too.
Yeah, of course. Thank you so much. And yeah, please feel free to give it a try. Please let us know if you have any feedback. Always happy to hear some.
Appreciate it. See you guys.
Right. Thank you.